Very good morning, one and all. We are learning the subject of the circuit theory or network analysis. And our chapter is the steady state or the transient steady state and transient response of the RLC circuit. So we have studied in the previous lectures that is about the steady state or sinusoidal RLC circuit. In that we have studied the introductory part or introduction, as well as we have gone through the numericals related to the series as well as the parallel connection of the sinusoidal RLC circuits. But today we will continue the transient responses. In that we will see the introductory part along with the numerical, how the RLC will be connected, what will be the effect of the transient. Okay, that we will see on the components when the components are connected. That is where the R, L, and C. Maybe the RL, maybe the RC, or maybe the R, L, and C. So see here the basic concepts which are related to the transient response. What is the need or what we need to take care while we are going to simplify the numerical on the transient, especially on the transient. What are the initial and the final conditions? What are the initial and final conditions? We remember we need to initialize, because in the beginning only I have told you, if you're talking about the steady state doesn't matter, but if you're talking about the transient, definitely the effect will be totally on the basis of the time. And on that time the t will be equals to 0, t will be equals to 0 minus, and t will be equals to 0 plus, and that you need to take care about the switches. That is nothing but whether your circuitry is open circuited or whether your circuitry is a closed one. How it is possible? With the help of the switch, that is you are going to open the switch or whether you are going to close the switch. If you are opening the switch, what will be the response? If you are going to close the switch, what will be the response? What will be the effect? So initial as well as the final conditions you need to apply before opening and closing the switches, that you need to take care, as well as you should remember the few steps, or you can say the procedure, before going to simplify the numericals. Okay, so that we will study, and at the end we will go for the numericals which will be related to the transient response. So if you are having a network, so how I can write my equation if I'm having the circuit, if the components are connected, or maybe the series or the parallel, doesn't matter here which connection is there, that is whether that is connected in series or the connected in parallel. But the important thing is that we are interested in the transient response. So definitely I need to write my equation while I will observe that circuitry, and the current will start to flow and the switch will be there, and depending upon that switch open and the close, the current will start to flow, and how I can write my equation, that is too important, how it will be. So see here, whenever you are writing any kind of network equation, so you should remember the circuitry which will be containing not only the resistor, inductor, and the capacitor, maybe the individual or maybe the combination, maybe the individual or maybe the combination. At that time, you should remember, we know very well the inductor and the capacitor and all the other things are the storing element, and to the inductor, capacitor, and the resistor, we are connecting the energy sources in the form of the voltage and the current sources. Okay, so current will be passed through with the components RLCs, and the voltage drop across the each component, and then we need to write the equation of the network, of a complete network, whenever the current is start to flow with respect to time period t, and if you are applying the voltage drop across that one voltage source with respect to time period. So what will be my equation that I should remember? Okay, so how I can write my equation? What will be the relationship between the voltage and the current while I'm going to write in the time domain? That is important. So in short, the characteristics, whatever you will observe while you are going to write, is nothing but VI characteristics with respect to the time. Time, that is nothing but in the time domain, you can say. So now one by one we will see here how wherever I'm connecting my source to the register, what will happen. If I'm connecting my inductor with the source, what will happen, and if I'm going to connect the source with the capacitor, what will happen, how I can write my equation. That is the voltage equation, that is the current equation with respect to the time period. So see here, one of the examples is mentioned here. The component R, the R component is connected along with your the source. That source is nothing but the voltage source with respect to the time period t. So that's why plus or minus is mentioned here. Polarities, okay. And we need to write the equation. So definitely, if the voltage source is across that component, that the current will, and the circuit is closed, then definitely the current will be start to flow in that register. So that current, that amount of a current will be I with respect to the time period t. So here we need to take it, that is every time we are writing the t, just because of that we are learning the transient response. We are interested in the transient. So we are talking about the with respect to the time period, or we are writing the equation of a relationship in the time domain. That's why every time we remember, just note down the t. Just note down the t whenever we are writing anything with voltage, with the current, anything. Okay, so now come to the point. If I'm interested to write the equation, so definitely what will be my Ohm's law? V is equals to IR, that you are aware from that. So V with respect to the time period, that is V of t, is equals to IR, that is I of t with the R component. So likewise, if inductor is there and that inductor is connected with the source, so definitely that source will be what the voltage, that is V of t, and the current will start to flow if the circuit is closed, the I of t. And how you can write the voltage drop across the inductor? Always be remember, voltage drop across the inductor V of t is equal to L into di by dt. See here, IR is there, so L will be here. Okay, IR is here for the resistor. So with the inductor, IR will be there. So di by dt, okay, the differential form. V of t is equal to L into di by dt. Similarly, for the capacitor, if I'm interested to write for the capacitor, so what will be my case? V of t is equals to 1 by C. Okay, 1 by C will be the case. So we remember, 1 by C integral of, okay, 1 by C if you are writing for the capacitor, so you should remember that we are interested to write your the what we can say, um, either the VC, or you can V of t, or you have the I of t. In all the cases, we should remember whether we are writing for the I of t or whether we are writing for the V of t. Okay, if you are writing for the inductor, see here the two cases are mentioned. If I am writing the equation for the inductor with the V of t, what will be the case? If I am writing my equation of L with respect to the I of t, what will happen? So see here, here the current is start to flow, no doubt at all, plus or minus. Already we are written the I will be at that moment t is equals to 0. Okay, the initial current is passing through that. Okay, initial current which is passing through that inductor will be 0 at the initial. So second time, if we are observing same amount of a current which the at t is equals to 0 at the initially, so how I can write my equation? That is mentioned, I of t is equals to 1 by L on the top, 1 by L integral of, okay, 1 by L integral of 0 to t, because t will be changed every time now, starting from the 0, but we don't know exactly for how much time period it will be there. So 1 by L integral of 0 to t V of t into dt plus I of 0. Why I have written here the I of 0 again? Because at the beginning I will be the 0, but every time that will be the change. Okay, so in this way, the V of t, in the previous slide you have seen V of t. In later on you can write the equation in the I of t. So likewise you can do, okay, likewise you can write the equation by observing the circuitry, whether you are writing for the voltage, whether you are writing for the current, that is too important. Similarly, if you talk about the capacitor, definitely the relationship between the V and the I in the time domain can be written here. See here, my capacitor is here, my I of t is flowing, and the V of t is across that. Okay, so how I can write that equation? I is equals to C into dV by dt. C into dV by dt. Already you have studied all these basic concepts which are related how I can write, because V is equals to IR, I is equals to V by R. So R instead of R, there will be the either the L or C, depending integral at the derivation form. So I of t will be C into dV by dt. Okay. So here, whenever the current will be flowing in the capacitor, so we are interested to take the voltage drop across that capacitor. Okay. Now, if I am going to write here V of t separate, so here C will be go to the denominator. So 1 by C will be the integral of 0 to t I of t of dt. So this I of t of dt will be here. This same equation we are converting, we are writing for the V of t. Once you write one of the equation, other you can find easily. I of t, if you are writing, so definitely V of t will be here, okay, at the right hand side, and the other will go in the left hand side, you can say. That is the one of C instead of this derivative form, integral form will be there, 0 to t. then this I of t will be the as it is, and dt will be the multiply with that, and the v at a 0, that is t is equals to 0, or v at a 0 initial voltage drop across the capacitor, that also we can find. So in this way, we should remember how the things are coming out, how we are writing the equation of a voltage, how we are going to write the equation of the current. That is too important. Now come to the point. While simplifying the numerical, one more thing we should remember. While we are simplifying any numerical, we should remember the few things, that is nothing but the initial conditions or the equivalent circuitry conditions. What is given in the circuit and what you are expecting and what is mentioned in the numerical. Okay, that is too important. Whether in the figure R is given, L is given, C is given, whether this symbolic representation of arrow and the I of 0 plus or minus of V0. This is too important. This will be the element with an initial condition. Whenever the word is coming, the initial. So at that time, definitely R will be as it is like this. L will be like this. C will be like this. I0 initial current will be like this. And for the capacitor across the V0. See here. At initial, the amount of a current which is flowing through the inductor will be I0. At initial condition, the voltage drop across the capacitor will be the V0. So that the symbolic representation is no doubt here is the capacitor, here is the inductor, no doubt. But whenever we are talking about the initial conditions, inductor, in the inductor, the current will be start to flow. That is nothing but my I0. In the at the initial condition, the capacitors across the voltage will be the V, that is nothing but the V0 plus or minus. But later on, if once the initial condition is over, because this we are talking about the transient means every time that is changing time, okay, we are changing with respect to the time period. So means we are not in the steady state mode, we are not in the constant mode, we are changing, the circuitry is changing every time from the 0 to, or you can say the 0 minus, then the 0, then the 0 plus. Three cases will be there. 0 minus means before the 0. 0 means at particular instant. Then 0 plus means once the switch is closed, what will happen? The current will start to flow instantaneously after closing that switch. So these are the cases: 0 minus, 0, 0 plus. So now see here how we can write the equivalent circuitry if the t is equal to 0 plus will be the case. This is the zero condition, you can say. So R will be as it is, no doubt at all. But we remember whenever the current, whenever the time period is 0 plus, okay, whenever the time period is 0 plus, at that time we should remember that where the inductor will be the open circuited, but your capacitor will be the short circuited. Okay, 0 plus means circuitry is switch. At that time, you should remember the inductor will be open circuit, capacitor will be the short circuit, and the amount of a current which is flowing through the inductor will be treated as I0, and for the voltage across the capacitor will be the V0. This concept will clear easily why you are going to simplify the numericals. Only just focus here how what are the changes are going on, what will be the effect. That's it. But while we will simplify the numerical, definitely you will get to know what are the changes are going on. So R will be as it is, L will be open circuit, capacitor will be short circuit, and the initial current, how initial current can be flow, the symbolic representation, and how the voltage drop across the capacitor in the symbolic representation. Similar to that, whenever you are having the t at infinite, the word which will come in while you are going to simplify the numerical and mention the time period is at infinite. So at that particular moment, when the mention clearly mention the time is infinite, so R will be the as it is, the inductor will be the short circuited, whereas the capacitor will be the open circuited. Okay, the initial current, how we can draw that in the, how the initial current will be passing here, just because of this SC, that is a short circuited current.